Okay, I think we're ready. So last time, what we did, we compared, or well, not compared, but we related stress and strain to each other. We drew a stress-strain plot. We talked about axial deformation. So we're still in the section of this course that deals with axial forces. So in that case, axial deformation meant stretching or compressing, something got longer or shorter. There was one thing that we forgot to talk about. Well, I forgot to talk about. And it's not a very lengthy topic, but we need to start out with that one just so we have it done. And what that is we did axial strain. So epsilon, we'll do that in a minute. Epsilon equals delta over original length, so change in length over original length. So it's just this ratio of how much something got longer or shorter. But we didn't do shear strain. So we need to talk about shear strain for a little bit before we move on to the next thing. So for shear strain, what we're going to do is we're going to remember why we had shear stress versus, get that in the right spot, shear stress versus axial stress. And remember, or normal stress, we called it both the same thing. Axial stress and normal stress meaning the same thing. We said that whenever we had an axial stress, the force causing the stress was normal or perpendicular to that area that the stress was on. And when that was not true, in our case, the force and the area were actually parallel to one another, that was a shear stress. Well, we have the same kind of thing talking about strain. So axial strain, something got longer or shorter. Shear strain is a little bit different. So shear strain is like this. Let's put us a piece of ground out here. So this is just something that our little box, we'll put a box on here. So this little box can sit, and actually it can be glued down. So like it's glued down to this ground. So the bottom won't move. So it's bolted or welded or adhesive of some sort. And let's put a shear force on the top of this thing. So we're going to put a shear force up here. So there's some force that's trying to push the block, but the bottom of the block can't move. And so what ends up happening, if we wait a little while, is something like this happens. Where's our bright color? Oops, not quite like that. I need it to go the other way. Oh, I don't want to. All right. Can I draw one the other way? There we go. So something like this, it skews. And this angle right in there, that is the shear strain. So how much did that previously vertical, it doesn't have to start out vertically. My example, this left edge is, it's perpendicular to the ground beforehand, but that doesn't have to be true for it to have a shear strain. It just means that angle changed. And this angle, we're going to call gamma. And that's going to be shear strain. Okay. And we can calculate it just by calculating that angle. So you have a length here. This could be our L naught or L or whatever we want to call it. And then technically it does get a little bit longer when it moves over, if the height stayed the same. We're ignoring all of that kind of stuff. And we're just kind of doing an average value here. We're also assuming that this line stays straight. It probably is a little bit curved. Ignoring all that. And we just want to calculate that angle, gamma. So gamma would equal, if I just turn that into a little triangle, I could do the inverse tangent of the opposite side, which is going to be, this is what I'll call my delta right there. opposite over adjacent, which is L naught. So I have the same kind of variables that I had before, but they mean a little bit different thing. So delta is how far did that top left corner, how far did it move over? And L naught is kind of the length of the side that that corner is on. So the interesting thing is that typically these are really small angle measurements, at least in radians, because it's not shearing. I mean, it's not doing a shear strain that's making this a very large change. So we can typically say that this is more or less equal to just delta over L naught. So as long as the angle gamma is in radians, which it normally is. So gamma in oh no, thank you, I put the wrong thing on there. That's all. Okay, so you heard me say this, but but here's what I actually wrote. I'll just go through it again so that you can see the thing. So on the left hand, I've got the unaffected box, right? And we put a shear force on the top of it. Thanks for putting in the chat. I saw stuff popping up, and like it's still popping up because the chat's like 20 or 30 seconds behind. So what we've got here is the box with the shear force on top of it, and the right hand side is the skewed box. So I guess I didn't show the force on top of there. There's still a force, pushing it over. And so what we're actually measuring is that gamma. So this little guy right here, this angle gamma, that is the shear strain. And so shear strain is, it's a change in angle. Whereas axial strain was a change in length. So that's a little bit different, and I did have some questions about that because there's a homework problem asking about shear strain, and we hadn't talked about it yet. So now you should be able to do that homework problem. All you do is take and calculate using an inverse tangent, or, well, that's what I was at when I saw the chat coming up. You can do the inverse tangent, delta over L naught, just figuring out this little triangle in here, this little guy. Or you can just take delta over L naught, because you're measuring gamma, shear strain, you're measuring it in radians. And the general rule is that when you have really tiny radians and you take the radian measures for an angle and you take the tangent of that, it's basically the same thing. So the tangent of 0.001 is 0.001. And it doesn't have to be that small of an angle, but that's the idea. So a lot of times, now I'm not saying web work is okay with this, because web work is very finicky on rounding and things like that. But if you're just doing a homework problem that's not web work, or a test problem, you can probably just take and do delta. How far did that little corner, I drew this little green corner on the top left, how far did it move over, and divide that by L naught, which is the length, how tall is that side, and that will get you the shear strain. If you want to be more precise for web work, then actually do the inverse tangent and find that angle in radians. So it does have to be in radians when you talk about this. It's not really a degree measure, it's a radian measure. So that's shear strain. It's pretty straightforward, but we didn't talk about it, so you didn't know how to do that. Speaking of other things, you've got 2 homework assignments. I am going to switch back over to the screen here now on purpose. You've got 2 homework assignments, homework 5 and 6. So 5 is more of the axial deformation, just more problems along that line. 6 is the new stuff for today. So why I point that out is that also today quiz 1 opened, And it would be good before quiz 1 stays open for a week, so you have a whole week to do it. And it would be good to at least do some of homework 5, not necessarily homework 6, but homework 5 before you take the quizzes, or quiz 1. The way these quizzes are set up is they're multiple choice. They are, I think this one might have 5 questions on it. And actually, some of these questions might be fill in the blank, and that's okay. There are some of those type of questions on the exam also. But these quiz 1, I would take it, you got an open book and everything, but I would take quiz 1 like it was an exam. So it counts for, I think, 1 or 2% of your final grade. I don't really remember. We'd have to check that out. But it's a small percentage of your final grade. And it's the simpler, like 1 or 2 step problems from the exam. So it's that style of problem. It's not the exact ones from the exam, but it's like that. So what I would do is I would do at least 2 or 3 of the homework 5 questions and all the ones before it. Take take quiz 1 as if you're doing an exam. So it's you've got your calculator and you're doing it like an exam. And it does have a 30-minute time limit on it, which should be plenty of time. And see how you do. If you make a C or better, then you're probably okay. If you make a B or better, then you're in good shape, because these questions on quiz 1 are gonna be simpler than some of the questions on the actual exam. So the actual exam will have questions like these, plus ones that are a little bit harder, and then plus a few that are a decent bit harder. So that's how I would handle quiz 1. Do some of homework 5, or the whole thing of homework 5, then do quiz 1 sometime in this week, and treat it like an exam and just see. It's more like a checkup to see how you're doing. If you make a D or a F or a 0 on quiz 1, then you really need to go do some more practice. So in your web work, remember you've got these optional practice problems, OP01. They don't count for anything, but they're simple and medium level problems that you can practice with. These challenging ones, they do count as bonus, but they are pretty complicated. And I think there's a lot of them. Let's see. Oh, I gotta log in. No, there's not. There's only 6 of them. There's a lot of the optional ones. I think that's what it is. Gotta log in again. Yeah, there's a whole bunch of these optional ones. These actually are problems mostly from the book also. So if you didn't do too well on quiz 1, then and you've done all your homework, you've completed all of the regular homework, go back and do some of the optional ones for practice, just to get up to speed on what you might be missing there, and ask questions. So definitely ask questions. We've got the Discord running. You can ask questions during the chat. Just realize in the chat it's going to be like 20 seconds before it actually comes to me. So there might be a little, I'm not ignoring you. There just might be a delay between when you write something and I actually say something about it. But that's totally fine. If there's a particular problem or question you have, let me know. All right. So the new stuff for today. What we're actually talking about today is we're moving into a combination of statics and strength of materials. So the static stuff is going to be this topic called method of joints for trusses. And then the strength of materials will be, okay, if we figure out all these trusses are like structures that have a certain configuration. We'll talk about this little picture I had. This is a truss bridge. So you see all these little triangles. Oh, no, you don't. There you go. You see all these little triangles in there. That would be a truss bridge. And we want to be able to figure out what's the force in all these little pieces of this bridge so that we can properly size the pieces so that it doesn't break. And that would be the statics. That would be the strength of materials part. The statics part would be figuring out the forces. The strength of materials part would be figuring out how big does stuff have to be, or is it going to break? Is it going to bend? Stuff like that. So we need to talk about some of these things for a bit. So let's add a space here so we have some room. All right, so we're going to begin talking about trusses. Actually, no. We're not going to talk about trusses yet. We're about to. There is a thing we need to talk about first, and that's the fact that we've been dealing with concurrent force systems. And that's been good. It's nice, summation of forces in the x direction, in the y direction, maybe in the z direction. They all add to 0. For it to be concurrent, all of the lines of actions for our forces, these forces were usually in cables and struts and stuff like that. They all intersected at one point. So we had little diagrams like this where there's some kind of a ring, and it's got some cables coming off of it with forces, and we've been doing that. But what if this ring was actually attached to some kind of beam, and this is my little I-beam that we're drawing, and it needs another support. So I need another ring over here. Let's change our forces to red. I like the red arrows for force. So it needs another force over here, and the beam probably weighs something. Now, all these lines of action don't intersect at one point. So I've got two that are parallel, so they're not going to intersect in a regular coordinate system. And then I've got these two angled ones over here. They intersect with each other, but I've got these other forces on my free body diagram also. So this is a non-concurrent force system. And all of our stuff that we do with these bridges and truss structures are the whole thing is going to be non-concurrent. We're going to be able to look at each one of these little places where stuff is joined together and treat those as concurrent force systems, but the whole truss as one big build or structure is not concurrent. So we got to be able to deal with these non-concurrent force systems. So on the concurrent side, we had 3 equations. And we hardly ever used this last equation, but we did use it some. That's a z. So what these equations did is they kept the free body diagram from translating, so it didn't move around in x, y, or z. The free body does not translate, and that was fine. But there's another thing that can happen in addition to translating, and that is rotating. So something could stay still, like this pen still, but it's rotating. It's not translating, but it's rotating. Or maybe it's like this, and it's rotating, but it's not actually translating and rotating or anything like that. It's just staying in one spot, rotating. And so when I have a non-concurrent force system, that rotation wants to happen. And so I have to add another equilibrium equation, and it looks like all these others, except it's this. So summation of m equals 0. So the m is called a moment, and a moment is a particular type of thing, like a subset of a torque. So you can think, in fact, if you're thinking of this from a physics point of view, they just do torques. Everything's a torque. But an engineering point of view, we kind of reserve torques for a very particular thing and moments as a more general thing. So for us, when we talk about torques, we're really talking about a shaft that's spinning and delivering some kind of power. And moment is the same thing, but it's not going to be used, the word is not going to be used when we're talking about axles and shafts delivering power. we're talking about everything else that has to rotate. We're going to call that a moment. So what this says is that the summation of all of these moments, and we're mostly going to treat these moments in 2D. So we're not thinking of things like spinning all in 6 degrees of freedom, moving around and spin. We're not thinking of that's too much for what we're doing right now. So we're really thinking of like a plane, a planar surface, and the object, in this case our little I-beam, spinning, rotating in that plane. But the summation of moments is that all of the forces that would want to make this thing rotate have to add, their moments, not the forces, but the moments they create have to add to 0. So we need to be able to calculate a moment. Might need some more space. All right. So let's look at calculating moments. There again, early on, maybe even the first day, we talked about we could do some of this stuff using vectors, and we could do that for these moments also. But again, what we're going to do is we're going to use rectangular coordinates, so x's and y's, to calculate our moments. So what we're going to say is that a moment is equal to a force times a perpendicular distance. We're gonna limit it to perpendicular. So we're not doing the vector things where we could deal with them a little bit differently. We're gonna say that this is a perpendicular distance to the force, perpendicular to the force. So let's how can we do? Let's just create a little box. And let's say that this is actually some kind of beam attached to a wall, and we put a force on there. So we want to know what moment is this force, let's cause it to be 50 pounds. What moment is that 50-pound force creating at the wall? So like right there. So that's an important concept with moments, is that we have to define where are we even talking about this moment. So I could have this 150-pound force, and it creates moments about all sorts of different points. So I have to choose, in my equation, I have to choose what point am I talking about. And it's not a wrong one to do. It's not like if you pick one point, it makes the problem wrong. That's not the case, but there are better ones to do. So there are some that are going to be way better than others to choose. For now, I'll kind of have to lead you on which ones make the most sense for the moment. Well, but when you write this equation, how I would write this equation, let's call this point A. How I would write this equation is the summation of moments about point A equals, and I don't know what it equals. You know, it equals the moment at A. We'll have to calculate that. I need to also specify what is positive and negative. So when I draw a force like these over here, these little arrows, we are normally assuming that X is positive when it goes right and Y is positive when it goes up. But moments, they don't go right or left or up or down. They go clockwise or counterclockwise. And so I have to choose in my little equation I'm writing here which one is going to be clockwise and which one is going to be counterclockwise. Now, the standard, there's a rule, a right-hand rule. We'll get into that later. We don't need it right now. And so that's going to usually mean that counterclockwise is positive. But looking at this problem, I'm actually going to define clockwise positive. And my equation up here, I wrote it equals 0. That's if I have a system that's in equilibrium. I don't really know if this system that I've drawn is in equilibrium. I mean, it probably is because it looks like it's attached to this wall. But that's a little beyond what I want to do right now. So I just want to know what is the moment created at A. And I said a moment is a force times the perpendicular distance. So the force is the 50 pounds, and it has a line of action that is vertical. So I have to multiply the 50. I'm not going to write an X because I don't want it to be confused with a cross product, which would create a moment also, but I don't want to confuse that. I've got a vertical line of action, so the distance needs to be perpendicular to this line of action. So it's going to be a horizontal distance so that they're perpendicular to one another. And let's just call that 1, 2, 3, 4, 5. Let's call that 6 inches. I don't know why that cursor keeps showing on there. So 6 inches. And so the total there, the moment that the 50-pound force creates about point A is 300 inch-pounds. So you're going to have units for moments and torques that are inch-pounds, foot-pounds, Newton meters, stuff like that. And I would, instead of writing a plus or minus sign on there, I would either say that, oh, it's clockwise, or I could do 300 inch-pounds, and I could write CW for clockwise. I need to indicate which way is it going. Whereas when you have a force, you pretty much, it's going to be positive if it goes to the right, or maybe the positive is determined if it's tension or compression. And so you might have to write tension or compression on things. We'll do that in a minute. But normally I need to put in one of these symbols, either a clockwise arrow or a counterclockwise arrow, or CW or CCW for counterclockwise. All right, so how does this help me with these things? So what this does is it lets me calculate the reactions. So let's do that for a little bit. Let's put some more space, and let's create not a truss yet. Let's just do I made a really simple bridge. So it's just a beam that I laid across, like a piece of wood that I laid across a river or something. And so it's just this. Okay. Now it has to be supported somewhere. I have two particular types of supports that I'm going to be using for these trusses. We'll add more as the quarter goes on, but I'm going to have what's called a pin, and when I draw it, it's going to look, most of the time it's going to look like this, a little triangle, and the triangle might be sitting on the ground. And the other one is going to be a roller, and it's going to be a circle that I might draw sitting on the ground. So that's the pin and roller. That might not seem like how this is held up, Actually, I don't know how well y'all can see on your screens, but if you look at this corner over here, you can actually kind of make out what looks like it could be a pin over there. And we can't see this corner over on this side. So that would look more like this triangle, but here there's actually a round pin that could be. It's kind of hard to make out on the picture here. But what this reasoning here is that a pin, if I drew a pin, how it might actually look would be something like this. There's some kind of clevis there, and then I've got, something attached to it, and this thing is able to move around, right? It can swing around one way or the other. So what the pin is doing is it's constraining motion in left and right, up and down, but it's allowing this piece that I connected to it, this piece, it's allowing it to swing around it, like rotate around it. So when I have a pin, I have two reactions, and the reactions are perpendicular to each other. So normally I draw them as a reaction in the X direction and a reaction in the Y direction. They don't have to be drawn that way, but normally that's how they end up being. The roller, it might look like some kind of thing that's, it's attached to something, but it's on roller skates. So it's letting the thing spin around, if maybe I have a little bar connected to it also, So that bar can spin around, but it can also move left and right, or whatever the surface I've got it rolling on, because it's on these little roller skates. So it can move forwards and backwards. So it only provides one reaction. And that seems like, well, you know, if you're building a bridge, why don't you just like bolt both ends down? That would make more sense so it doesn't slide around. But in the real world, there's a need for metal objects in particular to be able to move around. If I constrain both ends and then we're out here, it's 100 degrees outside, and it's a metal thing between those, that thing's going to want to expand, and it's going to generate some extra stresses in there. And then that's going to be a big problem, right? So even in an actual bridge like this guy, there is some room for it to move around, to change length. And so we model that room, even though if there's not an actual piece that's on a roller skate somewhere, we model it that we have a roller somewhere. It may not be that one of the supports is really a roller. It might be that they're, you know, when you drive across a bridge and you hear the thumping sound, those are expansion joints where the decking can expand and contract when it gets hot and cold. So it's going to be a realistic thing. It's modeling a realistic thing, but you may not actually see a roller skate on a bridge somewhere. So what I'm going to do, all that to say, we're going to put a pin over here and a roller over here on my little beam bridge. Somebody asked if I have a hydraulic course. No, I don't have a hydraulics course. Any of that we do is just kind of embedded into maybe some of the pressure type things that we'll talk about, but there's not going to be much hydraulics at all in here. Let's see. So let's look at the little beam, and let's put a simple, just one. This is I'm standing in the middle of my little bridge, so let's put 200 pounds standing right there in the middle, and then let's put a distance here. That looks like 4 feet, and goes to there. There's another 4 feet. And what we want to do is we want to figure out what kind of reaction is happening at the pin and what kind of reaction is happening at the roller. We need to know that because those are forces that are being applied to this beam. So we need to know, if we want to deal with any kind of stresses in the beam, we need to know what all the forces on it are. So I see the 200 pounds. The beam itself probably weighs something. We're kind of ignoring that right now. And then, well, we need to know, what is the pin and roller doing? What are they doing? So I'm going at this really very slowly. So a lot of these steps, if you were working out a problem, would happen much faster. But hopefully we're going at it slow enough that we're building up some ability to do these quicker later on. So that picture that I just drew, that's not a free body diagram. If we were in class, I'd ask, why is it not a free body diagram? But since all you can do is chat, it's going to take you a while to actually answer that. So I'll go ahead and answer it. But think about, why is it not a free body diagram? It's not because it's not free. It's connected to a pin, which is connected to the ground, and it's connected to a roller, which is also connected to the ground. So it's not free. So I need to free it by... Now it's free. Now I need to replace everything that was touching it that's important. The pin and the roller are important because there's the things that are holding it up, so they definitely do something. I need to replace them with their reactions. So the pin has two reactions. Let's call that end A, and we'll call the roller end B. You're going to do that so that I can label these forces as AY and AX. So AY and AX, they're the reactions that the pin has on the beam. So AX and AY, I don't know what their values are. I just picked two directions For the pin, these reactions do have to be perpendicular to one another, and it's usually makes the most sense that X is horizontal and Y is vertical, but that's not always true. Probably 90-something% of the time it's true, particularly for this course. But I don't know anything other than I picked some directions up and to the right, and I put some labels on there. B only has one reaction because it's a roller, and B is letting the right end of the beam move left and right, but it's not letting it move up and down. So it's only got a reaction in the up and down direction. Then to complete it, I probably should go ahead and put the 4 feet, put that. Probably should also put in a coordinate system, although that's not as important, but that completes the free body diagram. So now I've got something more like a free body diagram. Let's see if we can get some room there. There we go. What I can do with this is I can take all of my equilibrium equations. So I can take summation of forces in the x direction equals 0. Summation of forces in the y direction equals 0. I'm not going to write z, but because there's no z forces here, but there would also be z. And summation of moments equals 0. So those three, if I have static equilibrium, I'm not in a dynamic situation where things actually are moving around, translating around, then these three plus the summation of forces in the z direction equals 0, they all have to be true, or else it's not in static equilibrium. So I can apply these equations in any order I want. I can look at this first one and just say, well, if all the forces in the x direction have to add to 0, AX has to be 0. Because it's the only one in the x direction. So if there's only one and they have to add to 0, it has to be 0. I can look at the y equation and I can say, well, I don't know, but I do know that AY plus BY must equal 200 pounds because there's 200 pounds going down. I totally picked the direction for AY and BY as going up. That might not be true, but that's the direction I picked. So according to my diagram, they have to add to 200. The moment one's a little bit different. So the moment one is I look at my free body diagram and I pick some point where I know that this beam that I've drawn is not rotating about that point. Now, it's not rotating about any point, but I have to define a single point to put my equation around. 80% of the time, the best place to do that is the pin. So the pin is right here at A. So most of the time, the best thing to do is say that, well, I want to define this summation of moments at A equals 0. I'm going to pick a direction again. Let's do clockwise positive, but usually counterclockwise is technically the correct direction to be positive. But I'm just going to say clockwise. Since I get to define it, I'm going to say clockwise is positive. And the summation of moments about A equals 0. So what that means is that this beam that I've drawn is not rotating about point A. So it's not, thinking of there actually being a pin there and this beam rotating about that pin. It's not doing that. So those are not happening. And it's staying flat. Now, I'm not thinking about it flexing or bending, so those aren't rotating. So it really could be, if I push on this hard enough, that it's going to bend, but that's not rotating. That's something different. That's actually in the middle of this quarter. We'll talk about that kind of thing. So we're assuming this thing stays perfectly rigid for now. So I write this equation. And I say, all right, every one of these forces, I can kind of leave AX out because I already decided it was 0. So I can kind of ignore that one. But these other three, AY, BY, and 200 pounds, I don't know that they're 0, so I have to deal with them. The combination of those three forces, they have to create moments that add to 0. So let's look at the 200-pound force since we have that number. 200 pounds That has a vertical line of action. So I need the horizontal distance between point A and that line of action, which is that distance right there, 4 feet. So 200 pounds times 4 feet. I have to decide if that's clockwise or counterclockwise because I need to write a plus or a minus sign over here. So how I do that is I isolate the one I'm looking at, the 200 pounds. I isolate that one. Imagine the beam, even if the beam is not built in a way where there's a pin there, that doesn't have anything to do with it. Imagine the beam being able to rotate about point A, and I'm doing point A because my equation told me to do point A. Imagine the beam able to rotate about point A. Would the 200 pounds make the beam go clockwise or counterclockwise around point A? So I'm looking at it, and it looks like it's going to make it go this way, which that's clockwise. I said clockwise is positive, so I give a plus sign to this moment. Okay, now I need to do BY. I'm saving AY for later. So BY, it has a vertical line of action. So it needs a horizontal distance between point A and that line of action. So that looks like it's going to be 8 feet. And isolating BY, thinking about my little beam being able to rotate about point A, if I look the way BY is drawn, now I drew that arrow. I could have drawn it incorrectly, but that's okay. It looks like it's going to go around this way. That's counterclockwise. So I need to give that a minus sign because I said that clockwise rotations were positive, and this one looks like it's going counterclockwise. Now AY. So AY, its line of action, well, it actually goes through point A. So if you ever end up in that scenario where the line of action for your force goes through the point that you're interested in, then that's force times 0 distance. So AY times 0 feet. So it doesn't need a plus or a minus because it's just going to be 0. That's kind of like you walk up to the door, and instead of pushing on the doorknob to open the door, you push on the hinges, and you know it doesn't swing open or closed, or it doesn't do anything because you're pushing on the part where you're trying to rotate it about, and that doesn't do anything. So you can get moments that actually add to 0 or create a 0 moment by having the force's line of action pass through the point where you're trying to calculate that moment. So that ends up just that whole term is 0. So it turns out that this 0 goes summation of moments about point A equals 0. So this 0 is these, that's where those are coming from. Okay, so that 0 equals 800. I'm just doing 200 pounds times 4 feet, so 800. I'm going to do it as foot-pounds. Normally you say foot-pounds instead of pound-feet, but it doesn't matter. It's just what you normally say. Minus BY times 8 feet. So let's get us some more space. So moving BY to the other side of the equal sign, BY times 8 feet equals 800 foot-pounds. Therefore, solve this equation. BY equals 800 foot-pounds divided by 8 feet is 100 pounds. Now, if you were paying attention to this problem and just looking at it, you could have not done any bit of calculation and you would have gotten this right. Because we have a, moved over there. We have a 200-pound force that's directly in the center of a 8-foot-long beam. So it only makes sense that there's 100 pounds supported on one end and 100 pounds supported on the other end of that 200 pounds. But this is the calculations that prove that. Another thing about this is this number that I calculated, by came out positive. And that's interesting, but what it means is that the arrow that I drew for by was drawn correctly. So this arrow right there, that arrow was drawn correctly. Had I calculated this and by came out to be negative 100 pounds, then what that would mean is I should have drawn the arrow going the opposite direction. So in this case, going down. All right. Now, to finish out this thing, I would need to go back and maybe go back to summation of forces in the y direction and say AY plus BY equals 200 pounds. Well, BY is 100. AY plus 100 pounds equals 200 pounds. Therefore, AY is also 100 pounds going up. That's what we're going to do with moments in relation to things like this. Now, I don't see any questions about that. So if any pop up, we'll come back to it. But we'll keep doing these. Like, we're going to write these equations, particularly this summation of moment equation, many times in the near future. So if you have a question, go ahead and ask it. But we are going to do a lot more of those. But what we need to do now is we need to deal with the idea of a truss. So we're going to limit ourselves in here to planar, or so two-dimensional planar trusses. So 2D planar trusses. You don't have to have planar trusses. These trusses could be in 3 dimensions. Like they could have members that are going in X, Y, and Z directions. But we're going to deal with 2D planar trusses. A couple of rules that we're going to need to help us define trusses. And one of them is that trusses are made of members, so that's a word, connected by frictionless pins. So pins is another key term there. Now, they're not actually made this way, at least not normally. If we look at this truss, well, if you go to this website down here, let's see, this one, you can actually see, here's what one of those joints looks like. So it's really a bunch of rivets. These are like the old school kind of rivets where you heat them up and push them in and then flatten them out. So that's really how these things are typically made in a truss bridge. Truss bridges are not as common as they used to be because they're not necessarily as efficient as some of the more modern types of bridges. But you'll still see trusses in general, maybe not truss bridges as much. At least not new truss bridges. But what this one's actually 1923, and it was kind of redone recently. Let's see, when did they redo this? I don't know. They redid it 2018. And they kind of reconstructed it the way it originally was. But anyway, this is kind of what these joints look like in real life. Is there's these big plates called gussets, and they've got a bunch of holes in them, and the truss members, in this case the members are these I-beam-ish looking pieces here, are riveted onto these gusset plates and held in place. That's more like what really happens. We're assuming that big connection there can be modeled as a frictionless pin. And it's generally kind of can be, because what happens is that you can even see it here. These, even though there are these big plates in here, this point right about here, actually right about where that rivet is laying, would be the center of this beam, this angled beam, and this kind of bottom beam, and there's another bottom one that's kind of cut off the picture there. And so that imaginary pin, the frictionless pin that we're assuming is there, is kind of right in the middle there. And so what it does is each of these joints, so that's another key word, made of members connected by frictionless pins at joints. So each of these joints is a concurrent force system. Now, you have a lot of these. So there's a lot of these joints all over the bridge, but each one of them is close to a concurrent force system. You do have these big gusset plates that hold everything together and stiffen it all up. But you model each one of these joints as a concurrent force system. A 2D, in this case, this would be a 2D planar truss. There are two of these trusses, actually. The one we see here, and then in the background you can kind of see the edge of the second one, you know, the other side of the bridge. So that's another 2D planar truss behind it. So that's, we're making some simplifying assumptions, but they're generally good enough for this. Now, a lot of modern ways of tackling truss structures is through computer simulations and things like that. We're doing more of the first pass at some of this stuff, doing it by hand, and understanding how it works to begin with. So truss that we're going to deal with is made of members. The members are typically straight. All of these are pretty much straight. They don't have to be. They can be curved and all fancy shaped, but typically they're straight, like these pieces in here. And those members are connected by frictionless pins. In the real world, they're not, but we model them like they're connected at frictionless pins, and then we call that connection point a joint. In general, we do one of two things with the weight. So each one of these pieces has, you know, it's made out of steel, it's relatively big, so there are hundreds of pounds at least for each one of these members. And we either ignore the member weight, or if it's just too big compared to the loads that we're applying to this thing, typically the loads are heavier, like you're driving cars across it and that's heavier than the individual little pieces of the bridge. But if you don't think it's okay to ignore the weight, what you do is you either ignore the member weight or apply half of weight at each end of the member. So that would look like, let's just draw a little piece of a truss. Here's one of my frictionless joints. There's the member. There's another frictionless joint. And let's say that member connecting between there is so heavy that I think I need to deal with the weight. You could imagine, you know, distributing that load all the way across there, because that would be, you know, that would be more realistic. But that is not how we're going to do it for trusses. There are other structures called frames and machines that we will do that way. But for trusses, what we're going to do is we're going to take half of the weight and put it there, and put the other half over there. So we'll do one of those things. Another little detail that we need to keep track of, not sure why this moved over, kind of did some weirdness. Another thing is that members only have two pins. So I don't know, can we see this on here? Wow, it's really tough to tell. I wonder if let's see if there's any good pictures on the webpage. Kind of. mean, you can't really tell here, but you can see the rivets. So you might think that maybe this bottom piece is all one big long beam, like just play one beam that goes across the whole bottom. And that might be how they made some of these, it's possible. But how we're modeling it is that each one of these members is only connected at 2 points. So up here and down here. This little diagonal one is here and in here. Even though we got all these little rivets and gussets and all that, we're modeling all of that as one connection point. So across the top here, this would be divided into 2 pieces. So this piece and this piece. So they'd be 2 separate pieces, and they're connected together at this joint between them. So that's another little detail that we have to keep track of when we're modeling these trusses. Now, like I said, we're going to do a thing called frames and machines later on, where that's not true, and that's going to be one of the distinctions between trusses and frames and machines. Okay, I think we have enough that we can do some calculating. So let's not deal with this one just yet. This one looks more complicated than what we want to deal with. Let's do a super simple truss. So let's get us some room right in there. And let's create just let's make a triangular truss. So this, and this. I'm going to draw circles to show the joints. Those are the frictionless pins. And I'm going to put a pin over on one end. The pin and roller don't have to be at the ends. I just need somewhere I need a pin, somewhere I need a roller to support our trusses. We're going to say that this is 4 feet. This is 4 feet. This height looks like 5 feet. That'll work out nice. And let's put a single force just right here. I mean, that doesn't make a whole lot of sense on why I would build it this way, but we're just learning. So this is what we're going to do. And let's make this, I don't know, 500 pounds. All right, so this is not a free body diagram because it's still connected to the pin and roller. As part of what I'm doing here, I can kind of cheat and just copy this whole thing and paste a new one right beside it and erase the pin and erase the roller and replace them with AY, AX, and normally when you label these things, you go around, bottom left is A, then you go around clockwise. So B, C, and D. So that looks like that would be CY. So I kind of cheated. What you don't want to do, and I know it's tempting to do this because you don't want to draw the thing twice, but say you said that, well, I just want to save some time, and I'm going to put AY right there and BY or CY on top of the roller and all that. That, okay, you save some time. What that might actually do is you come back and look at this, and it's a little unclear if there's a pin with another external force applied to it, like on top of that reaction, or if you are kind of saying that is the reaction from the pin. So it is much better, it takes longer, but it's much better to create an actual free body diagram, get rid of the pin and the roller, and put the pin reactions and the roller reactions on an actual free body diagram than trying to draw them on top of just a sketch or a diagram, not a free body diagram. So just be aware of that. All right, what we're going to do now is let us typically, the first thing to do is not always 100% true, but most of the time, the first thing to do once you've gotten your free body diagram, so the first thing is create your free body diagram. Once you've gotten that, the first thing to do is usually find the values for your reactions. So if we were writing down our steps here, number 1, draw the free body diagram. That's almost always for any engineering problem that you're going to solve, draw the relevant diagram with a free body diagram, control volume, electronic schematic, whatever the diagram is, draw the diagram first. And don't draw these tiny little ones either. Draw big enough ones that you can label things. So for statics and mechanics, draw the free body diagram is the first step. Number 2, and this is where, it might differ depending on the exact problem, but typically solve for external reactions. So AX, AY, and CY. And I'll put typically, because there are some cases where maybe you don't do this as the second step. All right. Oh, that's not going to do. Let's do insert some space. Okay, let's go back here. So for us, the reactions come from our 3 plus the z direction, which is not relevant in our 2D truss here, from our equilibrium equations. So let's do our easy one first. Summation of forces in the x direction equals 0, and therefore for this setup AX is 0, so we can just mark that guy out. Now it could be that 500 pounds was at some angle and not going straight down, and there would be a x reaction at AX, or maybe C is not rolling on a horizontal surface, but it's rolling on an incline. Then there's a reaction there too. It's because the reaction is perpendicular to the surface you're rolling on. I don't know if I specified that, but up here, this reaction for the roller, that reaction is perpendicular to the surface that you're rolling on. Okay? So if your surface happens to be at an incline, then your reaction is at the perpendicular angle to that. All right, but in this case, AX is 0 just by observation. If I write the y equation, I'll get AY plus CY equals 500. This is another one of those cases where everything's symmetric, so I know that CY is 250 and AY is 250, but I'm going to write the equation for practice. So I want to say summation of moments. I'm going to do point A. Most of the time, it's best to do the summation of moments about the pin, and the pin was at A. I'll say clockwise is positive. I've got 500 pounds times a 4-foot moment arm going clockwise about point A, and I've got CY times an 8-foot moment arm going counterclockwise about point A, so I gave it a negative sign. Therefore, when I solve that, CY ends up 250 pounds. Then I can write summation of forces in the y direction equals 0, and that would be AY. I typically like to write the equation based on the free body diagram and then plug in numbers. So AY plus CY, even though I just know what CY is, I want to put the variable CY. Minus 500 pounds equals 0, and if I solve that, it'll tell me that AY is also 250 pounds. Okay, so I mean that one really doesn't need all the equations because it's obvious, but just so we have them written down again. So after you get to that point, typically what I'm trying to do with these, if I've got a real structure out here, what I want to know is, well, under this loading condition, so in this case the loading condition is 500 pounds pointing straight down at point B, what are the forces in all the members? Or maybe what's the most force in any member or something like that, because I want to make sure that it's under whatever load I simulate that the truss is going to not collapse on me. So under this loading condition, 500 pounds in the middle, what are the member forces? So we're talking about a process in this case called method of joints. Next time we'll talk about a process called method of sections. But method of joints, it says to look at every joint individually. So every joint in the truss is a 2D in our case, but it could be 3D, is a concurrent force system. Okay, that's a result of all of these little assumptions we made earlier. So I guess I didn't write it out specifically. Let's write one right here beside it. It kind of comes out of this member weight thing also, or it's related to it. It doesn't come out of it. Forces can only be applied at joints. And what that means, or not what that means, what results when all of these things are true. Members are connected by frictionless pins at joints. We ignore the member weight. Forces can only be applied at the joints. Members only have 2 pins. What all that ends up meaning is, let's write it in blue, all members are 2 force members. So that is kind of an outcome of these assumptions. Or rules, if maybe they're not assumptions, maybe they're rules. And a 2 force member, we haven't really talked about what a 2 force member is. We've used them, but we haven't like explicitly said what they are. So let's see. We'll do that. So in the method of joints, and actually under method of sections as well, every member is I'm going to write 2 force member just to speed it up. And what that means is, so let's just take this member right here. So member, we'll call it AB. One of our rules was that members have 2 pins. Another thing we talked about was, pin. I can't get it to stop scrolling weirdly. Pins have 2 reactions. So if I take those 2 things, there's a pin at A and a pin at B, then, well, there's a reaction. There's 2 reactions at B and 2 reactions at A. So that's a lot of little forces to deal with for every piece of the truss. But when I know that every member is a 2 force member, I can have that same piece, A and B, and if that one is a 2 force member, then I know that the forces in that member are, well, I want to draw them this way, like this. So it's all tension or all compression. I drew that one in tension when the arrows point away from the object. And if they point towards the object, then it'd be a compressive force. I also know that it's 2 forces, but I know that this magnitude equals that magnitude. So they're the same thing. Just one of them's pulling from one end and the other's pulling from the opposite end. Or they're both pushing on opposite ends of each other. The other little thing, which doesn't show up too much, but it does happen, is that let's say that AB is some weird shape. If I can prove that AB is a 2 force member, whoops, that's an A. Then I can take and connect the dots between point A and B. And that's still the line of action. So I'll draw this one in compression. So even though AB is this weird S shape, I still know that the line of action is between points A and B, wherever they are. The two pins that are holding this member in place in my truss or in whatever it's in. Assuming that this member is a 2/4 member. We could write the number 2. That might make more sense or make it clearer. Do it like that. That might work better. Okay. All right. So assuming all that, I'm in the method of joints. I've got my reactions, my external reactions solved, AX, AY, CY. Every member in the truss is a 2/4 member because it's a truss. It follows all the rules for a truss. Basically, the rules for a truss are these. You know, the real rule is that each member only has 2 pins, and their forces are only applied at the joints. So I don't have any forces applied directly to the member. I don't have any force like this, you know, pushing on the member itself. Then it turns it into a frame. And we'll do frames, but that's later. So all of that, I pick, so I select one joint from my truss. So in this case I have A, B, C, and D. So I pick A, B, C, or D. I should have one, at least one, I should put at least in here, at least one known value. And no more than two unknown values. So looking at my free body diagram, I know AY, I know the 500 pounds, and I know CY. So I could pick joint A. I would know 2 things there. I would know AY and AX, even though AX is 0, I still know it. So I know those. And I would not know the value of member AB. So remember, this is A, here's B, C, D. So I would not know the value of member AB, and I would not know the value of member AD. But that falls into my rule. I have 2 unknowns and at least 1 known thing, so I could work from that one. Same thing with Z. It's symmetric, so I would know that. D, I don't know anything. I know that BD, AD, and D or CD are all connected there, but I don't know any of those values. B, I know 500 pounds, but then there's 3 things I don't know. AB, BC, and BD. I don't know any of those 3. So it looks like the best place to start would be either joint A or joint C. So let's just do joint A since I've already circled it. So let's get us some more room. And what you do at this point is select a joint, draw the free body diagram of that joint. So I'm just going to have a circle for A. I've got AY, which I solved for, was 250 pounds. So I'll put that on there. Oops. I don't know AD or AB, but part of my rules for trusses tell me that every member is a 2/4 member. So when I go to draw the AB force, I know that, well, here's AB, you know, it's headed off this way. And the force in that one, I don't know if it's tension or compression, but I know it's in this direction. And that's the force in AB. I'm going to draw it in tension And if I solve the equation and it turns out that it should have been in compression, what will happen is I'll solve FAB and it'll come out as a negative number. And I'm okay with that. And then there's this piece over here. And same thing. I don't know if it's tension or compression. Now you can get good enough to where you can look at these things and say, oh, AB is in compression, AD is in tension. But it's not necessary that you start out that way. It is totally fine to just know that there's a force in there, and those are two force members, and so you can just draw these arrows as tensile arrows pointing away from the little free body diagram that we drew, and let the math tell you if they're positive or negative. What's this one called? AD. Now I could put a coordinate system in there, right? So I could say that this is my x-axis for this local free body diagram, and that's y. Now I've got back to a concurrent force system. And so I'm back to doing what we were doing last week. And I have a 2D concurrent force system, so I write summation of forces. Now, if I think about it, if I write the x equation first, there are two unknowns in the x direction. AB has an x component, AD has an x component. But if I write the y equation, there's only one unknown, so I can actually solve for that. So sometimes it pays to take a few seconds and try to figure out, should I write the x equation or the y equation? If you can't figure it out, just pick one and write it, and if that doesn't work, write the next one. There's only two to write. So I'm going to write the y equation. So I just realized that I've got to figure out that angle because I need the y component. So let's go back to our diagram. I don't have that angle. It's this angle right here. But I do have this 4 and 5. So a rise of 5, a run of 4. So I'll put, instead of putting this on here, I'll put that. So I had a rise of 5, a run of 4. I could figure out my hypotenuse for that. So let's do that real quick. 4 squared plus 5 squared. Take the square root of those is 6.4. 6.403, so I'm just going to leave it at 6.4. All right, now we can go back to writing our equation. So I've got 250 pounds. That's easy. 250 pounds. It's going up, plus I've drawn the FAB going upwards and to the right. So plus FAB times the, well, depending on what angle I'm looking at, sine or cosine, but I'll use the sine of this angle, and I will use the definition. So 5 over 6.4. That is the cosine of, we'll call it theta, if that angle is theta. Not the cosine, sine. Sorry. Sine of theta. So if I were to go in and figure out, well, let's see. That angle would be inverse tangent, whoops, inverse tangent of 5 over 4. 51, so theta is 51 degrees. 51.34 degrees. If I go in and do the sine of that angle, that is sine of theta equals 0.7808. If I do 5 divided by 6.4, I get 0.781. So it's the same thing. So you can do that. You can go in, convert everything to degrees and, you know, angles, and do the sines and cosines based off that. That is completely fine. There will be some problems like this one where it's probably a little bit faster to just use the definition of sine and cosine like we did originally here with the 5 over 6.4, but it all comes out the same in the end. So that's up to you on what makes the most sense in your mind. Those are the only two, the 250 pounds and the y component of FAB. Those are the only two in the y direction, so they have to add to 0. So solving for FAB equals, I'm going to move the 250 to the other side so it comes out negative, and then divide it, the 5 over 6.4, which is that 0.781. So 250, negative 250, divided by 5 divided by 6.4. Got to make sure my parentheses are right. 320. Negative 320. So that negative sign is important. That means the arrow for FAB is drawn backwards. So it should be pointing towards my little free body diagram, which means FAB should be in compression. So when I write the actual answer, FAB equals 320 pounds, instead of putting positive and negative, because the positive and negative really don't mean tension and compression, they mean that your arrow was drawn the right way or not. I happen to draw my arrows in tension, so positive does mean tension and negative does mean compression, but not everybody does it that way. So what you should do is 320 pounds and then put a C behind it for compression, or a T for tension, instead of trying to put a negative sign on there. At that point, let's insert more space. At that point, we can write our X equation. So what time are we at? All right. I'm going to do this and one more thing, and we'll call it a day and come back Wednesday. So looking at my free body diagram, again, I'm usually not going to plug the values in until after I've written the equation based on the diagram. So according to the diagram, I've got FAD plus FAB, and I need the cosine, which would be the 4 over 6.4 equals 0. The 250 has no x component, so it doesn't go in this equation. Then I take my 320 pounds and I look at that. That's 320 pounds of compression. In my picture, I've shown it as tension, so that really needs to be a negative. That's why I like drawing all my arrows in tension when I don't know what they're supposed to be, because my negative signs are compression and my plus signs are tension. You don't have to do it that way. You just have to keep track of this stuff. So FAD minus 320 times 4 over 6.4 equals 0. FAD, when I move all that to the other side, it all becomes positive. 320 times 4 divided by 6.4 is 200. And we'll put the tension on there because it really is going in tension. So we've solved for that guy and that one. There's one other one I want to look at here that's interesting, and that is D. So let's look now at a free body diagram of joint D, and then we'll be done. So, free body diagram, joint D. So it's here. I've got a piece coming off here, piece coming off here, piece coming off here. I don't know this one, so I'm going to draw it as FBD. I do know this one. This is AD, right? It's just the other side of member AD, right? So I know that one end of AD is 200 pounds of tension, so that means both ends of it have to be 200 pounds of tension. The little confusing part is that tension isn't left and right. Tension is away from the body or towards the body. So tension is away from the body. So I'm going to draw it this way. 200 pounds, because that's FAD. And I don't know this one. This is CD. So I'm going to draw, all of those arrows are in tension. I know one of them. And, you know, almost immediately I can write, oh, well, summation of forces in the x direction equals 0. The way these are drawn, FCD minus, you know, I've got my coordinate system, x and y, minus because I'm writing summation of forces in the x direction. So even though AD is a positive tension, you know, as far as tension goes, it's a positive sign. In the x direction, it's going to the left. So you have to keep these separate, that tension is not automatically a plus or a minus or anything, particularly when you're doing forces in a certain direction. It's which way is your arrow going, you know, and my arrow is going to the left. I just wrote the x-axis is positive when it goes to the right, so this is a minus FAD. BD has no x component. I'll plug in my values, and therefore turns out FCD is also 200 pounds. You probably could have looked at that and determined that just without writing the equation, but we wanted to write it. The interesting one is this, though. Summation of forces in the y direction equals 0. So I'm looking at it, and, well, FBD plus nothing equals 0. So FBD is what's called a zero force member. All right, so we'll do that ZFM just to not have to write zero force member every time. And it doesn't mean that we can just totally leave it out of the truss, you know, just take out member BD. It just means that under this particular loading situation, with everything being rigid, so nothing deforms, nothing changes shape or anything like that, so it's under a very simplistic set of rules, also all of these rules here, that member BD doesn't have any force in it, or it's a really small amount of force. So essentially, as long as we keep everything the same, we don't move the 500 pounds, or we don't add, you know, if we add some more force to it, then it changes things. But if we don't do that, then, why can't I erase it? There we go. Then member BD could kind of be thought of as not even being there under this scenario. So that could be helpful if you could identify those just by looking at the truss. And it turns out you can. You can ID zero force members with a couple of rules. First, you find a joint with 3 members. So joint D had 3 members, AD, BD, and CD. Then you look at that joint, find 2 collinear members. So that means they're in the same direction. It doesn't it doesn't mean they're horizontal or vertical or anything like that. It just means that 2 members are in the same direction. So in our example, AD and CD are collinear. You know, they're on the same line of action. If those 2 first things were true, you found a joint with 3 members, 2 of them are collinear, then if there is no force at the joint, No, let me put that. No external force. So no external force applied, and I'm going to put directly. To the joint. And the joint I'm talking about is the very first one that you found the 3 members at. So no external force applied directly to that joint. The third member is 0 force. So let's look at some pictures. Well, maybe we can look at that truss and see if it has any 0 force members in it. I didn't look to see if it did or not. Let's see. No. Oh yeah, it does. Yeah, it does. So it's in fact it's got the same kind of 0 force member that that we have right here. So this joint right. Oh, let's draw with some color that's going to show up right here and right here. Those joints have 2 collinear. You know, the bottom pieces are collinear. Let's see. That's collinear. Those 2 are collinear, and that one are collinear. There's no force. You know, there's no force applied right here. That doesn't exist. So this third piece, this little guy, is a 0 force member, and so is this one, 0 force member. Under assuming that there's no force applied at that joint. You know, I don't know where the forces are going to be applied on this bridge or whatever, but assuming you don't put a force like right there or right there, then that green one that I colored in is a 0 force member. All right, let's draw something over here and pick out some 0 force members. Let's make this let's make this a pin. And we'll make a roller over here. And we'll connect some piece there. And let's connect a little piece here. There. There. And let's do this. I'm trying to draw it kind of like it's made up of individual little pieces so that it's more clear. And then we need some diagonals in there. One thing about trusses is that they're going to be made up of all triangles. So all the shapes inside here are going to be triangles. If you have a shape that's not a triangle, then it's not a it's not a stable truss. It might flop around. So they do need to be all triangulated to be a truss. All right, let's put a single force over here. Now, this roller is applying a force over here, and this pin is applying a force here and here. And let's just do A, B, C, D, E, F, and G. All right, so I'm looking at my joints with 3 members. A and F have 3 members. A does not have any collinear members, so it's not going to have a 0 force member there. F does have 2 collinear members, so EF is collinear with FG. There's no external force applied at F. It doesn't even matter. Like if I put a force up here, let's add that force. That force is not applied at F. That force is applied at D. So there's no force applied at F. So this guy is a 0 force member. DF is a 0 force member. If you haven't picked up on it, whenever you talk about the members, you typically alphabetize their pins to name them. So instead of member FD, it's member DF. Totally doesn't matter, but that's typically what you do. Once you find a 0 force member, repeat the process. So take that one out mentally. So take out DF repeat the process now, well, now D does have 3 members. 2 of them are collinear. Let's take this guy off of here because I want to prove a point. So let's take that off. Doesn't change what we had previously done. 2 of them are collinear. CD is collinear with DE. And there's no, now that I've erased it, there's no force applied at D. No external force applied at D. So DG is a zero force member. And G has 3 members, 2 collinear. FG and AG are collinear. No force at G. This one, CG, is zero force. So it turns out that all of these in this middle are zero force members. It doesn't mean you can just take them out and the truss behaves exactly the same as it would before, because they are there for stability purposes. As soon as, well, let's look at this. Where did I draw it? Where did I draw it? As soon as AD and CD are not collinear, you know, maybe something deforms and it looks kind of like this. This is extreme, but does that. All of a sudden that BD is not a 2 force member. There are forces in the Y direction, so it can support some load. So it's not that you can just take these pieces out, but under the exact loading condition you have, when you calculate them, they will calculate to have 0 force in them. One other instance of a 0 force member, and let's see. I'm going to copy this thing and use it. All right, so let's take the force off at E. And let's put it over here. Well, no, yeah, that's fine. Now none of those are zero. Those are not 0 force members now, right? They're actually doing something. So, draw it as a member though. So since I put that force at F, then DF is not a 0 force member, which means there are not 3 members at D, which means that, you know, it's chain reaction, these are all suddenly doing stuff now. But over here at E, this doesn't really fall into the rules that we wrote, but anytime you have 2 members, DE and EF, that come to a point and there's no force there, those are both 0 force members. No force there, those are both 0 force members. So these two end up being 0 force members, and you can kind of tell just by looking at it because there's no force over there other than the weight of the pieces themselves. So that's another condition for 0 force members. 2 members at a joint, no external force at that joint. What that means is both are 0 force members under that loading condition or setup. All right, so what you need to do, homework 6 is the beginning of trusses. I would go ahead and, you know, do 1 or 2 of those. I think there may be 6 problems in there. Don't get behind on the web work because it does, you know, every day we get another, or every class day we get another web work thing to do. So try to do 1 or 2 of the simple ones just to, you know, reinforce some of this stuff. Do some of homework 5, take quiz 1, take it like an exam so you kind of get a feel for where you're at on content wise, realizing that the questions on the quiz are the simpler questions on the exam. So if you're having trouble with those, then you need to go back and practice more. If they're pretty obvious, then you're probably on pace for, you know, certainly a passing grade on exam 1. There will be a little bit more complicated things on exam 1 also. So do some, you know, do a lot of that web work practice. I will say the challenging problems are way more complicated than anything is going to be on the exam. So if you're breezing through the challenging web work problems, then the exam should be totally fine. because there's none of the exam problems are going to be at the level of the challenging problems. They're pretty intense usually. All right, we'll be back on Wednesday. We'll do some more trusses. If you have questions or maybe a web work problem that we need to work through, we can do that. We're going to do something called the method of sections on Wednesday. So it's another process like method of joints. I will see y'all then.